Hello again, pre-calculus students. Let's continue our lesson on hyperbolas. Share my screen with you here. And here we go. So, what we have in this lesson, this is on page 717 of the textbook we're using as I'm making this video. I want to find the equation of a hyperbola that has these two asymptotes and these two vertices. So to find the center of the hyperbola, which I need for my HK value, I just set these two y values equal to each other, solve for x, solve for y. So my hyperbola is centered over here at 6, 2. That's just the intersection point of the two asymptotes. We also know that the slope of the asymptotes are positive 2/3 and negative 2/3, so that's going to be helpful. We know that the center is at 6, 2, the vertices are at 3, 2, and 9, 2, so 3, 2, 6, 2, 9, 2 would be off to the right. So I know it's going to be something like this green equation here. It's going to be an x minus h squared over an a squared minus y minus k squared over b squared equals 1. Because I know that the vertices are here and off to the right, and the center's here, I know that it's going to open left and right. So that's how I know that x comes first. So I already know that h is 6 and k is 2. I know that a is 3. The only other thing I need is b squared. Well, look at the graph and look at the what you can tell here. The slope is the slope in this case a over b or b over a? Well, I hope you got it correct that it's b, plus or minus b over a. And because the slope is going to be y over x, so it's going to be b over a. Well, the slope is 2/3. So b over a, b over 3, because we know a is 3. B over a is equal to 2/3. That makes b equal to 2. B squared then is 4. So now we have the equation of our hyperbola. It's x minus 6 squared over 9 minus y minus 2 squared over 4 equals 1. So the key points here were to first find the center, find where the two asymptotes intersected, and then using our vertices, determining does the hyperbola open left, right, or up, down. In this case, we were able to see that it opened left, right. So we know what the equation is. And then using the a value that we can get from the center to a vertices, we were able to solve for b. Now, I've told you before that the general equation of a conic can be written with these 6 variables, a through f. But for our purposes, we're going to let b equal to 0 because we don't want to take a curve and rotate it. So if your curve is a conic, then if it's a circle, a must equal c. If it's a conic and one of the other, a or c, is 0 but not both, then it will be a parabola. If a and c are of the same sign, but they're unequal, if it's a conic at all, it'll be an ellipse. And if A and C have opposite signs, which means that their product is negative, then your conic will be a hyperbola. Now, again, that's assuming that they are conics. They could be degenerates, or in a couple of cases, no graph at all. So here's a fun question I like to ask. And this one can be a little bit I don't want to say it's tricky, because nothing in math is tricky, but it could be non-intuitive. And since I can't tell where my picture is, we'll just put it here for now. Let's say that you have a conic in general form, which for us is going to be ax squared plus cy squared plus dx plus ey plus f equals 0. And let's say that a and c are of opposite signs, so it's going to be a hyperbola. Can you tell by looking if that hyperbola is going to open left, right, or up, down? And the answer is, unless you're a genius, no. So let's take a look at this equation. And you might be inclined to say, well, it's an x squared minus y squared, so it should be open left, right. I'm going to show you that in this case, it's going to open up, down. That's why you can't just go by looking here. Also, I don't know if they still have these on the SAT, but a common question was to give you something like that and say, what is this graph? And everybody go, ooh, hyperbola. Well, for a hyperbola, that would work. But if this was a plus here, you might go, ooh, ellipse. And, well, even a hyperbola, I guess, could be a degenerate. You could get those two intersecting lines. But even if it was a plus there and it was an ellipse, you could be a degenerate ellipse, which is a point, or it could be no solution at all, which would be, an x squared over something plus y squared over something equal to negative number. So in general, you cannot tell just by looking. You have to go through the process of completing the square and do a little more work before you can tell. So let's go back to this one. It looks like it's going to be a hyperbola, and since it's an x squared minus y squared, it looks like it's going to open left, right. Let's continue. So I group the x's, the x squared and the x together, and I factor a 4 out. So there's my x squared plus 2x, and all that times 4. And to complete the square, I have to add a 1 in there. Take half of the 2 and square it. But I didn't really add 1 to the left side of the equal sign. I added 4 times 1. So let's see, this 4 up here gets moved over, and then I have to add this 4 that I added in. Now here I group the y squared and the 6y. I factor a negative 1 out. So I have y squared plus 6y. And to complete the square, I take half of 6 and square it. But I didn't add 9. I added negative 1 times 9 to the left side of the equal sign. So I have negative 9 that I have to add to both sides to keep it balanced. So when I factor this, it's called completing the square. That means I could make it a perfect square. Same here. And it's still x squared minus y squared, but when I divide by that negative 9, nifty things happen. Well, I have 4x squared over negative 9. That's the same as, x something squared over negative 9/4, because dividing by negative 9/4 is the same as multiplying by negative 4/9. And then I have this negative divided by this negative gives me a positive. So if I were to rewrite this, this is going to be a y squared. Here's my minus over here, an x squared. So in this case, the hyperbola opens up, down. So again, you cannot tell just by looking. You have to do a little more work and get it into this standard form, at least most of us. Some of you are geniuses. Maybe you're able to look at this and All that just happens naturally. For us mere mortals, now we have to work at it. Wait a minute. A 2015 Raider mug, yay. Same with an ellipse. Like here, you might look at this equation and go, okay, that's x squared plus y squared. They're the same sign, different values. So it's automatically an ellipse. Not so fast. If we complete the square, we group the x's together, factor out the 4, complete the square, we're adding 1 in here times 4. So I have to add a 1 times 4 over here. I group the y squared and the y term. I have to add a 9 times 1 is 9 to the left, add 9 to the right. I have a negative value. Now I have something x squared plus something y squared equals a negative. There's no solution. And what was the big change here? It was this 1,000. If this were plus 13 instead of plus 1,000, if it were exactly equal to 13, this would be a negative 13 here. We'd add 13 would be 0. This would be 0. Then we would have a point, a degenerate ellipse. It would be the point -1, 3. And if it were -1, 3, you could see that would be 0. This would be 0. This would be -13 plus 13 would be 0. Yeah, it would be a point. And if this number is anything less than 13, you bring it over here to the other side, and all of a sudden, by adding this 13 on here, we're going to be having a positive number. So everything hinges on this f value. So just wanted to share that with you so that you don't, in your zeal to apply a rule, saying, oh, okay, they're different, they're the same sign, different values, it's an ellipse. Always have to consider those other possibilities. Now let's talk about asymptotes of a hyperbola. Because this is kind of nifty. There we go. So here's a hyperbola. It's an x squared minus a y squared, so it opens left, right. The center is at 3, -2, 3, -2. And it's y over x, so b over a. B is 4, a is 2, because remember this is b squared and a squared. So 4 over 2 is 2. So the slopes of the asymptotes are plus or minus 2. So to get this slope, you can see I went 1, 2, 3, 4, up 4 over 2. That's a slope of 2. Because this is 4 and 2. 4 squared, 2 squared. So anyway, here's my box. Here are my asymptotes. What are the equations of these green lines, these asymptotes? Well, we know they're slopes. This one is +2. This one is -2. We're going to do something a little different than you've probably ever done before. Not much. We are going to use the point slope form of the line. And remember, point slope form of a line says y minus y sub 1 equals a slope times x minus x sub 1. Well, we could write the equations of both of these slopes, write them separately, put them in slope-intercept form, but nobody cares. In fact, that's even more difficult than what we're going to do. Will you agree that there is one point on both of those lines? And it's that point right there, the center, 3, -2. So we can write the equation of the slopes, the asymptotes in point slope form. Y minus -2 equals a +2 or a -2 times x minus 3. So by writing the equation of the asymptotes in point slope form, we can do both lines at once just by making that slope plus or minus 2. So we don't have to write two equations, and we don't even have to put it in slope intercept form, which should make everyone happy. So that's all I have for this video. Hope you got some fun algebra out of that, and have a great day.